Okay, welcome back to Precision Machine Design 2.75x. This is the second lecture for Topic 1. Topic 1, remember, is we're talking about the philosophy of design and how we start organizing our thoughts. Deterministic, wild, crazy. And now we're going to get into some very specific operating mode, particularly working with a design team, even if the team is only you and yourself. And there's a very certain structure that goes through, and we'll explain the dynamics of this in a minute. And you may have noticed something else between this segment and the previous one from Topic 1. Yes, you're correct. The shirt has changed. And notice in Topic 1 we had all the seasons. And on this topic here, we have, when you zoom in and you look at the fine atomic features, you'll see sheep. Why are we using sheep for this motif? That can be a bonus question you will find out at the end. But for now, we'll deal with sheep. Everyone think to yourself, how do you think about design? Remember our drill press example. Things about the drill press that may annoy you. Oh yeah, I'm really upset about that, so you know what? I've got this really great idea. I'm going to take the drill press and I'm going to add a fuseloffer, and that's going to go up and down, and let's see, I can put some gears here. Oh, this is so brilliant. Oh, and it's going to go along, and it's going to look like Alien, and the tongue will come out, and if there's a person over here who's not drilling correctly, it'll penetrate his brain, implant a little creature, which will then grow up to create a new, better drill press. Fantastic. Sell it. So you see, the problem with that is I went into a little bit too much detail too fast. Okay? So we're going to take a step back and we're going to talk about how can you efficiently create a new concept or a new idea. Because remember, you're born something else and you're here, click. And really good designers, their minds are just full of ideas, and that can be your own worst enemy. So to help you focus, we're going to do the following things. We want to say design approach is we're going to be deterministic. So we want you to be wild and crazy, but we want you to think in a structured manner while being wild and crazy and using your physics. Remember, we're going to get to the analysis later. But go coarse to fine. And what that means is we're going to develop a strategy to approach the problem. We're going to pick the best strategy to create a better thingy, and then we're going to create concepts for it. Okay? So, for example, for our drill press, we look at the drill press and we learn everything we can about it. That's part of the background or history. And they say, what is going to be our strategy to make a better drill press? And let's just say, for example, our strategy is, when we're using the machine, what makes us the most unhappy is the table and positioning in part of on the table. We want to come up with, you see, that's a strategy. Our strategy for making a better drill press is to do the table, make the table better. Another strategy is, fix the part and do everything with the head. The head moves and drills the hole. That's a different strategy. When you're looking at an idea or a problem area, you'll come up with several different overall approaches to make the thing better. And notice in both of those things I just said, like strategy 1 and strategy 2, I didn't really say how I was going to make the head do everything or what I was going to do in the table. All I noticed is my approach to making a better product is a better table. Once you decide with your team or yourself, often by what's the biggest bang for the buck, what the best strategy or approach to something is, then you start developing concepts. Let's say I'm going to pick the table. My strategy for releasing a better drill press is to have a better table. Now in the concept phase, you say, well, what's wrong with the table? Well, here's this table, and it's really crunchy to go up and down, and this happens a lot. If I'm drilling a hole in the part, and then I've got another hole evenly spaced over. I've got to unclamp the part and move it over and hope it stays aligned, and then drill the hole again. Like if I go to swing the table, it's on an arc. And notice when I go to swing it, whoa, that's not very good. So how would I make it so it goes up and down yet swings to position the part where I want? So now I start developing the idea of concepts. And what are different concepts for that, how to do the table? You can start with the idea of part, drill, and notice what I'm doing here, I'm sketching real fast, and we'll get a lot more into this in topic 2 about some of these techniques. And in future topics, we'll talk about things like what's called the structural loop. So these are things why it can be good to read ahead. Structural loop being the flow of forces through the machine, just like in circuits, the flow of current through a circuit. But different concepts for the table start with, I need to take the part and move it. How can I move it? I can move it linear, rotary. That's where you start building up actual physical hardware concepts to implement the strategy. And again, we're going to be doing a lot more detail on this. This is the overall approach and picture we're doing. Once you have the concept you like, and let's say we'll pick, here's 2 concepts, for example. One concept for the table is, if I'm looking down on the drill press, I'm going to have an arm and then another arm that comes out, and this is looking down on it, remember, here is the table. So this becomes a dashed line. And then now I position the table by moving these 2 arms, like this. This is a concept here of, these are called revolute joints. Another idea is, well, here is looking down on it again. Here's the column. And now I'm going to have crossed axes. So this axis moves up and down this way, and then it goes back and forth that way. This is like the table on a milling machine. And here is where my part lives that I'm going to drill holes in. Okay, this is a Cartesian system. So you see, both of these machines accomplish the same function of moving the part around underneath the drill so I can put a hole in it, but they use very different components. So we're going to be going through, how would you decide what's best? And then when you decide what's best, how you take this thing all the way to the detailed product phase. So I can launch the product. So I got part drawings I'm releasing. Now, we need a little more structure because our brain is still going off on too many random tangents. For each step of the strategy or the concept or down in the modules and components, you still need one more layer of how to think about the strategy, for example. And I love to make fun of acronyms. So this is called FRDPARRC. We normally have 3-letter acronyms, but 3 letters is boring. Why not just use a herd of letters? Which is a 3-letter acronym, by the way, HOL, HAL, herd of letters. Okay? These, I would hypothesize, are the 6 most basic things that you gotta have when you're thinking about a design. And you want to burn these ideas into your head, so whenever you think of something, you just FRDPARRC it always. Whoop! These are the functional requirements, or the events. What does the thing have to do? What does it do? That's the functional requirement. The design parameters, or the idea, is how does it do it? Back here, what does it have to do? It has to position the part. That's the functional requirement. How does it do it? Well, it's got revolute joints on an arm. Or it's got Cartesian joints. Everybody loves to do this part. You're going to really love to do this part too, the analysis. And why are you getting thinking, oh my God, physics, analysis, equations, This is where you really make your mark. Because as you're thinking early on, you start doing the analysis of, wow, I've got to move this to move the part on the drill, but how? And there's three types of things. Accuracy, and then you've got repeatability or precision, same thing, and then resolution. Accuracy is if this thing was controlled, how well can you make it go to the position you want? Repeatability would be how well it comes back. And resolution is if it's here and my drill, I'll use the microscope here, blow this up, and here is where I want to drill my hole. But the drill bit is over here. Can I move the table under this, or the slightest little motion, and whoop, the table moves over here. And now you get into this hunting business. How do I write the equations and do the analysis to make sure the mechanism will do what I want it to do? Okay? This particular machine here, and it's loose, it goes down nicely. Gravity's working with you, but it doesn't go up so nicely. I would hypothesize that someone did not do their analysis right on there. That can lose a sale, all right? References. Where has this been done in the past? There's very, 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 very few things that are totally ultra double extra new. Most stuff builds on the past. There's a new combination of things, but the actual things you're combining are probably been there before. You'll modify them with your analysis, but you need to understand where things came from and how best to modify them. And then there's risk. Ask yourself for everything you're thinking about, what could go wrong? And whenever you think of what could go wrong, come back and ask yourself the countermeasure. How do I make it right? And as I'll show you pretty soon, often that is just do the complete opposite. Okay? So these 6 things, whenever you think of some cool idea and your brain is going a mile a minute, what does it do? How am I going to do it? How am I going to do the analysis to optimize this to maximize the return on investment? Or can I hire a geek somewhere to do that analysis, but knowing that you have to do the analysis? Okay, calm down. I know I'm brilliant and really, 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 really good looking and well dressed. But there might have been someone else who actually had the same idea before. We better make sure that we're not just reinventing the wheel. Because there have been a lot of other really, really, really good-looking, well-dressed people in the past, too. And then the risk. Okay, build this thing. I release as a product. Now, me as a user, how would I abuse it? What stupid human trick would I do that might hurt myself or someone else or the product? How could it fail? Countermeasure. Calm down. Okay. The handle can't turn going up. The gearbox is icky. How can I fix that? So rather than fix it afterwards when the customer brings it back screaming, fix the gearbox in the early stage of design. Okay, so you see we get wild, crazy, and then you calm, focused, and go back. And cover these 6 things. There are other things you may want to look at, but these are the basic 6. An example in the text was dinner. You know, what's your strategy? You're going to eat in, you're going to have takeout food, you're going to have it delivered, or you're just going to go to a restaurant. Okay? What's your strategy? Let's say we're going to do delivery. We want to eat by food being delivered to my house. Okay. What kind of food? This is on the concept phase. Pizza, Chinese food, burgers, subs. You know, what do you want? Okay. Down on the components level, let's say we pick pizza. What do you want on your pizza? Everything toppings? See, everything can be sliced from coarse to fine, right? Design, you got to remember, is a whole series of steps. You think from coarse, strategy, to fine, picking the actual parts and putting the dimensions on the drawing. These are 10 steps. There may be 15, there may be 3. Don't worry ever about any design strategy, design philosophy. be careful about taking things too literally, because if you only do things one way, you may miss the other way. So your mind should always be open to learn and think about new ways of thinking about things. You can go through these 10 steps and maybe more. So the first thing is take resources that are available, stock of it, remember Maudslay's maxims. Study the problem and figure out the scoring. How are you going to win? Make sure you have a clear understanding of how to win, how your device will succeed or not. The third step, start with strategies. Fourth step, having picked a strategy, concepts. Fifth step, now you take your concept, you break it up into modules. Back here, my modules are the joints, and ideally they're scaled, so it's all really the same part, just different scaling. That's one module is the joints. Another module is the actual arm structure. And a third module is the actual table. Once you've broken up into modules, you'll pick your most critical module. What's the hardest thing to do? Let me do the hardest thing first. And then you go and pick components, whether they're out of a catalog or you're designing parts that you're going to machine yourself. Seventh step is that detailed engineering, manufacturing review, design review, always cycling back. Does it meet the goals of the customer, the initial functional requirements that were set for the machine? Then you have detailed drawings as an 8th step, 9th step, build, test, modify. And the proviso for the build, test, modify is feel free from steps 1 to 8. If you're unsure of something, design, build, make a mechanism, a toy mechanism, a sketch model. We'll go through that in a little more detail. But for example, on a precision coupling, you're really not sure how it's going to go together. Remember, you're a tactile animal. Make it and touch it and feel it. And oh yeah, that works just great. And oh look, here's a failure mode. One of the balls broke off. Make sure in the real design you don't do that. We'll fix that later. Okay? Make models. Use Legos. Use real parts. Feel free as you're systematically, deterministically, carefully, structurally thinking of things. Blah! Go play. Wee! Wah! So you want to be working this dual personality. 1, it's more productive. B, it's more fun. Okay? And C, it's more productive. And D, it's more fun. You see, it keeps cycling. Okay? 10th step. Fully document the process and you create your service manuals. Now, people love to create. People usually don't like to write down. So you have your design notebook, okay? And your design notebook will have your name and email in it. So when you leave it in the airplane in the back of the seat pocket, someone will email you and say, I found your design notebook. And then you've got designs, dated, signed, documented, all kinds of fun stuff. And comments from others, okay? So this is what we're going to be using as our design notebooks and going through the details in this class, as you should have your own design notebooks. Now, let's go through some of those steps. A little fast. Resource assessment. Time, money, materials and components that are available, and manufacturing processes. Those are the 3 big elements of resources. The physical stuff, the human stuff, and then the cut and put it together stuff. Figure out what you got available. And you're going to have to design within the contents of those bounds. Understanding the problem. Remember, there are no problems, only opportunities. Understanding the problem will mean physically going and playing with the thing, if you can, that is causing the opportunity. Really get to know it. Remember, you're a tactile creature. Use your senses. Simple drawings, sketches, and a very important thing, first order analysis. Let me give you an example of that. When I drill a hole, most holes are to be positioned, and let's just, we're going to pick this guy, the Revolute joint design. When I position this, if the table in this position is horizontal, and as I move it, the table is then at an angle, because of the slop in the joints. Why would it might do that? Well, let's look a little bit more carefully at a joint. A revolute joint will have an axle or a pivot, and then it'll have the top structure, for example, that is snug and there's zero clearance and maybe even glued in there. The lower arm, the arm that pivots off of that one, they will be some sort of bearing material. And then there will be the arm that comes off of it. Now notice I'm drawing the arm a little bit wacko. And there's some clearance in here. There has to be clearance because it moves. If it's preloaded so it's zero clearance, there'll be friction. So how much do we allow? Call that delta. And the height of this bearing here is h. And the diameter is, of the big shaft here, is d. When you go to drill a hole, you have a certain perpendicularity requirement. The customer expects things to be perpendicular. As I move this part, when I go to clamp it, is it always going to clamp in the same way or not? I don't know, but let's do a first order estimate of what is this angle here and does that matter? The angle alpha to the first order, we'll assume a small angle approximation here, is going to be what? Very rough approximation. If this height is much larger than this diameter by factor of 1.6 to 3, for example, and you're going to see where those special numbers come from, then we can first order approximate this angle alpha is around delta over h. Delta may be, for reasonable things, 0.1 millimeters. H may be 50 millimeters. Is that a good or bad angle? What is that angle? You calculate it. You tell me, if I have my part here, what that means. That's what topic 3 is going to go through a lot. And what that means is a little hint. If I have a block of something I want to drill a hole through, and I want the hole to enter in the center of the part, and I hope that the hole on the backside also exits out the center of the part, but it's coming in at an angle that's off by 0.1 millimeters over 50 millimeters, and this part is 100 millimeters tall. Guess how much off your hole is going to be down here. 0.2 millimeters. Is that bad? Depends what the drill press is wanting to do. This is the type, and this is a very simple analysis, but it's actually really effective. The type you want to do when you're first thinking about problems and in your design notebook is you're coming up with these brilliant concepts. Be doing this type of first order thinking, which will help you start to early on differentiate between the potential goodness of concepts and help you pick the concept that in the end will be engineeringable. That's the key, because remember, born, start project, you hope to finish the project here so you can go snowboarding. You don't want to be working the project out here at the end, okay? So that's our first order physics. Words. Words are like physics, because without words, you don't have physics. This is, sound of one hand clapping, not very loud. Words make physics be heard, so you can do something with it, okay? You need to be able to describe in words what you did and why. That's really critical for patents, for warranty work, because you may win the lottery and decide and go off and become a fashion model, and the next person has to pick up where you left off. Okay, strategies. So we went through strategies already. Review it again. Remember, you develop strategies, play, draw, read, write, do calculations. Write calculations, read, play, draw. Mix it up. If you went through this one way in your office, working on something, okay, I'm going to follow the recipe to do this. Then go to the gym, get your running stuff on, and go for a run or a swim or a walk. And then approach it from a completely different aspect, in a completely different environment. Liberate and free your neurons to new ways of doing things. Because, remember, you're following this very structured approach and you're very smart. Your competition is going to think, we know that these guys are very structured and smart and they're systematic about thinking about things. There's no way we can compete against them because they wear Hawaiian shirts. Okay, let's just go for a run. We'll do something totally wacko different. Maybe we'll figure out something. Okay, so remember that you might as well go ahead and do the complete opposite of what you normally would do because your competition is going to do that and try to defeat you. Okay, plus it's more fun to do it that way. Remember, defeat. Use your feet. In the text, it goes through another example here of a precision linear motion system. That would be used, for example, on the table axis. And notice all this scribbling here. We're going to get to that again. And what does this mean? And why? This is actual pieces from one of my design notebooks earlier on. And here's the first order analysis and some references and risks and countermeasures. This is from my actual design notebook, systematically going through this FRDPARRC process. So in your design notebooks, you should be writing down, here are the functional requirements, what I want to do, here are the design parameters, how I think I'm going to do them. Here's the analysis, physics in words, analysis in equations, references, where I got the ideas from, the risks and the countermeasures. Force yourself to write it down and go through it. So another example of strategies. We're not going to go through in all the detail here. We're just going to go through different, make sure you remember you have different functional requirements. For each different functional requirement of the machine, what is the mechanism, the thingy that's going to do it? These are often form the modules of your machine. Okay. Given that you've picked a strategy, how do you now come up with all the different concepts? Remember we had the revolute joint and the translational joint for the drill press. Watch what happened. Sketches, first order analysis, words, the same kind of thought process we apply again. These processes can be applied over and over again from the coarse to the fine level of design. Oh, here's this precision linear motion example again. See, we took the earlier creation of the strategy, how we wanted to approach it, and now we're taking it apart in detailed concept. And when you look at the slide, you'll notice we actually start getting into a lot more detail on the analysis, a finer grain. Just the way the design process itself goes from coarse to fine, the amount of detail you do in the analysis and the drawing and stuff also goes more and more detailed. When you take the strategy, the design parameters are how you're going to do the functional requirement, how the strategy meets the functional requirement, actually ends up becoming the functional requirements for the concepts. That's a very interesting little trait you'll find. That if I start off with, I need a better way to drill parts, holes in parts. That's my functional requirement for my strategy. My design parameter for my drill press to meet that functional requirement was make a better table. So good, I'm going to focus on tables. Now, when I go to do the concepts, the functional requirement is better table. And now how do I make a better table? For example, then I'm going to take this arm, revolute or linear, and I'm going to focus on how I actually make it better. Revolute joint, tight. See, we did the analysis earlier. Tight bearings. And then later on as I get into components, how do I make that bearing tolerance go to 0 for no cost? That's what we'll learn in later on lectures in the class. So remember, the design parameters for the concept are going to then be used as the function requirements for the components. Just the way the function requirements for the concept came from the strategies, design parameters. Modules. Once you have your concept, you break it up into modules, as we talked about earlier in terms of the joint is a module, the arm is a module. Same process. Words to describe the drawing, or excuse me, the module. Do some drawings, do some first order analysis, do some play. Help it develop ideas and get the thoughts out of your head. Here we took the idea of a concept, break it up into modules. Again, each module will have what do you want to do, how do you think you want to do it, what's the analysis I need to do for that module. For example, here we did the analysis of this joint module. What are the references? Where I got this out of the fundamentals notes, for example, or I've seen these kind of clamping collars. What are the risks? What are the countermeasures? What's a risk in this design you see here? You're shy like me, I can tell. The risk is when I loosen this up to move this arm, there's this little thing called gravity, and whoom, this thing falls on the floor. Wow. That would be bad. I know. I can add another part here with an... There, I fixed it. That's the countermeasure. But that costs money. What's a better solution, maybe? Make that gravity. Literally, the risk was this thing could slide off and fall on the floor, plunk, and hurt somebody. The countermeasure is make it so it doesn't slide off. Gravity is going the other way. In other words, I flip this mechanism, and the arm comes off the top. So that's kind of one of our first lessons that will come out of from topic 3, the process of reciprocity. Often, your countermeasure equals 1 over your risk. Both philosophically and literally. Components. Notice the person here is a scuba diver. Now, Jacques Cousteau was one of the inventors of the aqualung. He had the idea of putting a cylinder of compressed gas on your back, and then first stage, go from high pressure air to low pressure air, and then breathe out the other end. Brilliant idea. Fantastic. Launch the product. But if your tank can't hold high enough pressure, such as this watermelon, you ain't going to make very much money. Okay, so the most brilliant idea in the world can fail because of one little thing that goes wrong. One wire that isn't placed right, that abrades and causes a spark, can cause a huge fire and destroy an entire thing. Everything has to be right. You don't get partial credit in the real world for a lot of things, especially where safety is concerned. Okay? So you've got to have the right components. And the way you get them is model them, do the math, do the physics. This is why you do the engineering classes. And you understand things, and you build the code, you follow standards. Okay? Back to, remember the design parameters for the module become the function requirements for the components. Process repeats. Every single component, what do you have to do? How does it do it? What's the analysis, references, risks, countermeasures? The process repeats. And what you'll find is the more you actually do design, the patterns from the process repeat, just like this shirt. They go over and over, and together they form a beautiful, wonderful machine or fashion. Okay? And every now and then in the pattern, you'll notice something interesting. All these sheep, and if anybody can find the one that's most interesting, that's the interesting part. So in the pattern, patterns are not boring. There's often hidden surprises that can be really wonderful. But you don't want the surprise that ain't so wonderful. Okay? So focus on your process, stay passionate, look at the analysis, experience, risks, countermeasures, who's done it before. You can enter in this loop from any point, just always complete the loop. Always complete the whole process. Okay? So our next topic will be further on ideation, how to work in teams, how to build diversity and get the best possible product and not miss anything.